So I am going to just run us through the steps that we would go through if we were running our own test trying to find out if two things are associated or not. So this is about the chi-squared test of independence, and it tests just that. It tests whether two variables are associated or independent. So the first thing that we're going to do in a chi-squared test is we're going to write down what our null hypothesis is and what our alternate hypothesis is. And the next thing we're going to do before we do anything else is we're going to choose our significance level. And so your significance level is basically what percent of the time your results will be due to chance rather than due to an actual association or independence. Meaning, for example, let's say that I ran a test trying to find out if hair color and eye color were associated. And let's say I found out that they were associated. Well, if I ran my test at the 5% significance level, it means that 5% of the time the test came out like that because of a random chance rather than it came out like that because the variables are actually associated. So, choosing how do you pick a 1%, 5%, or 10%, it's really based on what you're studying. Imagine if you are testing this new heart valve for, its effectiveness, and this is in the medical field, then you're probably going to choose the 1% or even smaller than that, right? You have to be really sure of your results if you're doing anything with medicine because, you don't want to chance any kind of mistakes, anything like that. But let's say I'm just trying to find out for, out of curiosity, is your sex, male or female, associated with your performance in math class, and you're just wondering, then 10% or 5% would be perfectly acceptable. So you're going to choose your significance level first before you do anything else. That's so that you don't manipulate do your whole test and then say, oh, well, if I use the 5%, it'll work out the way I want it to. No, you have to choose your significance level first. Okay, then you're going to find your expected values. Then you're going to check the validity of your test. And then you're going to find your chi-squared calculated value. You're going to compare your calculated value to your critical value, and that's going to tell you whether you accept or reject your null. And then you're going to analyze your results. Why do you think your results were what they were? Did they surprise you? Did they fall in line with what you expected from just looking at your data or using other simple math processes? If you were going to do it again, what would you do the same or differently, or what might you want to extend this idea using? Would you want to take this one step further, etc.? Okay, so here's going to be our sample data, and so we said that the first thing that we're going to do with our data is we are going to write a null and alternate hypothesis, and so I'm just going to kind of move this out of the way for a second, and to find our null hypothesis, our null is always going to state that your two variables are independent or not associated. So it looks like from my data, I'm trying to tell is your sex, male or female, associated with how many meals you eat per day. So my null hypothesis is going to say that sex is independent of number of meals per day. And my alternate hypothesis is going to say that someone's sex is associated with number of meals per day. Okay, once I've done that, I'm going to choose a significance level. This is something that's interesting. I don't need it to be perfectly accurate, but I'd like it to be accurate, so I'm going to choose a 5% significance level. And notice I'm choosing that before I do anything else. Okay, the next thing I'm going to do is I am going to find my expected frequencies. I have right here my formula for finding the expected frequencies. We're going to take the row total times the column total and divide by the sample total. So in order to find what my expected frequency would be for males eating 3 or fewer meals per day, I'm going to look at my male column, and my male total is 55. I'm going to multiply that times the column, this column right here, the total is 27. And I'm going to divide that by our sample size total, which is over here, and that's 100. And so when I do that, 55, which is the row total, times 27, which is the column total, divided by 100, and I get 14.85. And basically that's what we're saying is that if my data were proportional to the number of males I have versus the number of females I have and how many people I have eating 3 meals, 4 or 5 meals, or more than 5, then we would expect 14.85 males to eat 3 or fewer meals per day. And so that's what that expected value is saying. And so then I'm going to find my next expected value. Again, I'm going to look at the 55 males times the column total of 45 people eating 4 or 5 meals a day, divided by the sample total of 100. And so when we do that, we have 55 times 45 divided by 100 gives us 24.75 for our expected value. Okay, and we're going to continue this process on and complete all the rest of these expected values. Okay, and so once we have completely filled in the table, you'll notice that your totals should be exactly the same totals as you got from your observed frequencies. They should line up exactly the same. We also need to find out how many degrees of freedom we have. And so our degrees of freedom is going to be the the number of rows minus 1 times the number of columns minus 1. And that does not include the total row or the total column. So we can see that we have 2 rows here. And so that's 2 minus 1. And we can see that we have 3 columns right here. And so that's 3 minus 1. So that's 2 minus 1 is 1. 3 minus 1 is 2. So that's 2 degrees of freedom. Okay. And we are going to use that degrees of freedom in order to find our critical value. One last thing before we go and find our critical value, we do need to double check that our expected frequencies are all large enough that our test is valid. And so one thing that we might want to look at, or that we need to look at, is these expected values right here. And so the rule says that none of these expected values can be less than 1. And so, we can check each one of them, and as we look, none of them are less than 1, so we're good there. And then the other thing that the rule says in order for this test to be valid is it says that no more than 20% of the expected values could be between 1 and 5. And so we have 6 expected values. And so that means that no more than one of those expected values, because no more than 20% of the 6, so no more than one of them could be between 1 and 5. The good news is that when we look at this, every single one of these is more than 5, so that we can say that, oh, there is a valid test, this is a valid test, and we can go ahead and move on and find our critical value. So here's our critical values table, and when we are trying to figure out what is our critical value, we're going to look at our degrees of freedom down the left-hand side, and we are going to look at the significance levels across the top. And so in this example, we said we were going to do, I'm going to zoom in here, we said that we were going to do 2 degrees of freedom. That's not that we were going to do, but that's what we found, that there were 2 degrees of freedom. And we said we were going to use the 5% significance level. 5% written as a decimal is 0.05. And so we're just going to read over and down, and that gives us our critical value of 5.991. So we already figured out that our chi-squared critical value was 5.991. And now what we're going to do is we're going to find our chi-squared calculated value. Sometimes that's called our chi-squared statistic. And you can represent it by using the chi-squared symbol with a subscript of CALC for calculated. And that chi-squared calculated value, or that chi-squared statistic, can be found by finding the sum of, and you're going to subtract the observed minus the expected squared divided by the expected. And so we are going to do that for every single pair of observed and expected values. So here's one pair of observed and expected. Here's another. Here's another. Here's another. You guys get the idea. And for each of those 6 pairs, we are going to go ahead and calculate the observed minus the expected squared divided by the expected. Okay, so we are going to go ahead and say, all right, what is our first observed value? Our first observed value is 15, and our first expected value is 14.85. We're going to find that difference, square it, and then divide by that expected value. And then we're going to do that again for the next observed and expected value. So that's 25 and 24.75 squared and divided by the expected value. And then we're going to do that for the next one, 15 minus 15.40 squared and divided by the expected value. And the next one, which is 12 minus 12.15 squared divided by the expected value. And the next one, which is 20 minus 20.25 squared, all divided by 20.25. And 13 minus 12.60 squared and divided by the expected value. And that is going to give us our chi-squared calculated. So once we had set that all up with our observed minus our expected squared divided by our expected, we take the sum of each one of those results, and that will give us our chi-squared statistic, or our chi-squared calculated value. So when I did that, I got 0.0548 when rounded to 3 significant figures. So for our chi-squared calculated value, we got 0.0548. And for our chi-squared critical value, if you remember from a couple slides before, we had gotten 5.991. And so we're going to take those two values and compare them. And as we can see, this calculated statistic is less than our critical value. So that goes along with this right here. Our calculated statistic is less than our critical value, so we're going to accept our null. And accepting our null, remember that our null hypothesis said that a person's sex and how many meals they ate per day were independent. And so since we're accepting that null hypothesis, we're saying that yes, they are indeed independent, they are not associated. Had we had a chi-squared calculated statistic that was greater than the chi-squared critical value, then we would be able to reject the null hypothesis. And if that were the case, that would say that the two variables were associated. And so that's how we decide whether the two variables are independent or if they are associated. So to summarize, I just want to look back at what we did. We started out by identifying our null hypothesis and our alternate hypothesis using the language or terminology of is independent or not associated, or dependent or associated. Those are the terminologies that IB accepts. Once we did that, we chose a significance level, and we did that before we really played around with our data because we didn't want it to be manipulated. Then we calculated our expected values, and we checked our validity, okay, with our expected values, making sure that we had no more than 20% of the expected values below 5. And then we found our chi-squared calculated statistic by using the observed values and the expected values. Once we had the calculated statistic, we compared that to the critical value, which we would get by using our significance level and our degrees of freedom. And that tells us whether to accept or reject our null hypothesis. And then lastly, we haven't talked about this, but analyze. So we're going to think about our chi-squared test that we just ran. And one thing that's really important to note is that what we did right now is we found out that there was no association between a person's sex and the number of meals that they ate per day. Let's say that there had been an association between the two. Even if there is an association, the chi-squared test only tells us that the two variables are dependent or independent in this case, but it only tells us if they are dependent or independent. It does not tell us causation, and there's no statistical test that can really tell us causation. So let's say that we ran a test on hair color and eye color, and we found out that they were associated, and maybe we figured out that the people who had darker hair were associated with having darker eyes. So let's just say that was what our outcome was. Even if that was the association that the chi-squared test told us, we wouldn't be able to say, oh, having dark hair causes dark eyes, or vice versa. We couldn't say that having dark eyes causes someone to have dark hair. It's just a relationship. It's just a association, but it's not that one thing caused the other thing. So we have to be really careful when we're analyzing that to make sure that we are talking about the association as a relationship, but not as a causation. Now, part of analyzing also includes thinking about why you think the results came out the way that they did. And it's okay to kind of come up with some possible reasons why your test either came out the way that you expected it to, or why it didn't come out the way that you expected it to. So, for example, let's say you ran this test and you were positive that the two variables were going to be associated, and then you run this test and you find out that they're not, that they are independent. Why is it that you think that the results came out the way that they did? And you are going to come up with some ideas. Was it because maybe there was some error in the way that you collected your data that caused some bias, and so maybe your data isn't completely valid? Or is it because you feel like maybe you had a limited sample, and so it really, you were doing this study about driving habits and you only focused on juniors who were driving, but really, your sample was really limited because, first of all, there's seniors that are driving, and then there's also this whole world of adults in college and beyond who are driving, and so maybe it just wasn't a good representation of the average driver. So you just have to kind of give it some thought. Why do you think the results either make sense as to what you expected, or why do you think they came out differently? And it's okay to kind of come up with some possible reasons. And once you think about that, that should lead you into the kind of last part of an analysis, which is if you were either going to do this test again, or if you're happy with, how you put together your test and wanted to do an extension on your test, what would you do next? So, let's say you feel like, hey, maybe the way you collected your data wasn't totally valid. What could you have done differently to improve that? And it's okay to have not collected your data perfectly as long as you're analyzing and admitting and being transparent with that. Or let's say you're really happy with how you collected your data and you feel like the test went really well, but now you're wondering, okay, well, I found out that this isn't associated, so I wonder what is causing high ACT scores. So maybe you want to do a different test checking the association between high ACT scores and something else. So how might you extend this project? So analyzing is kind of your last step, but it's very, very important to kind of reflect on what you did, what was good about it, what might you do differently, and kind of where you might go from here. If you want to reference any of the material that we talked about in this podcast, it's all found in chapter 13 of your textbooks. So you're welcome to go ahead and check in chapter 13 and work some extra problems and let me know if you have questions.